Good morning and welcome everyone. Thank you for joining us today as we begin the second week of our April webinar series. My name is Adam Galata. I'm the Marketing Manager for the EMEA region at Monolithic Power Systems. Today I'm joined by Jens Hedrich, our Senior Field Applications Engineer and EMC expert in Southeast Germany. He'll be presenting EMC Optimized Buck Converter Layout. Before we get started, if you have any questions during the presentation, please type them into the question box in your Zoom control panel. These questions will be read aloud at the end of the presentation during our Q&A session and will stay anonymous. All of our webinars are available for on-demand streaming on monolithicpower.com. Today's webinar will be added shortly after the presentation. I will also send out a follow-up email with links to the presentation materials. Now let's get started with the presentation and turn it over to Jens.
Hello, everybody. Welcome to our webinar about EMC Optimized Buck Converter Layout. My name is Jens Hedrich. I'm working since 2010 as Senior FAE for Monolithic Power Systems in Central Europe. I'm supporting industrial and automotive customers on their power supply designs. And I have a special focus on layout and EMC topics, including frequently troubleshooting visits to EMC labs with our customers and our own boards for optimization and improving the performance. Before MPS, I was 11 years at Linear Technology and at Nokia Mobile Phones as hardware design engineer. The agenda for today, we will have a look at initial system setup and PCB partitioning. We will have a discussion of component placement and the layer stacking. And we look into the classic debate, copper under the inductor, yes or no. And then we go through an example case study of a buck converter layout that is good but not optimum, and see step-by-step improvements of the EMC performance. At the end, I have a few frequently asked questions that I answer, and then I like to answer and try to answer all your questions that you enter during the session. Our motivation is to avoid exactly this kind of EMC debacle, 50 dBs above the CISPA 25 EMC conducted emission limits. This is an old example from 2010, a 7M 30 volt synchronous buck converter. The board was not optimized for EMC performance, but for thermal. We see a huge switch node on the top side and the bottom side. It's acting as cooling heatsink for the inductor and for the IC. There is only two layers, so there's no solid ground plane under the DC-DC block to provide area for eddy currents, and of course there are no input EMC filters to clean the input. Here's a much better board, our MPQ 4430, a 3.5 amp 40 volt synchronous buck converter. This board is set to 480 kilohertz with spread spectrum, and you can see that the EMC performance is extremely good. We have a huge headroom even to the stringent OEM limits. For example, here in the FM band, 12 dB microvolt average, and we are 8 dB below this. This board was discussed in detail in a former webinar that is still available on our website. Let's refresh for today the buck converter voltage and current waveforms. So our buck converter consists of a high side and a low side switch. They are PWM controlled in a way that at the switch node, we get an average voltage of the desired V out. But of course, we have high amplitude V in with high dVdt. The current waveform in the inductor is triangular. It's a continuous current waveform, which is more EMC friendly. If we look at the current waveform in the high side switch, we see a trapezoidal shape with very high dIdt. And similar current waveform we see in the low side MOSFET, and also we see discontinuous current waveforms with high dIdt in the input capacitor. So the very critical point is a so-called hot loop, the two switching MOSFETs and the input capacitor. They should be placed as close together as possible. For our EMC performance, the high dVdt means E-field radiation. So this increases this input voltage. So the higher the V in, the higher the E-field radiation, but it also increases with the antenna size and height above PCB. This is mainly the inductor, which is connected to the switch node and acts as E-field antenna. The high DIDT means H-field, so magnetic field radiation. This, of course, increases with current. The higher our output current, the higher the amplitude of the current and the stronger the magnetic field. And it also increases with the antenna loop size and the height above the PCB. So again, the key point is to minimize the loop between the switching elements and the input capacitor. A reminder from a former webinar, magnetic antennas. So if we think of our hot loop placed above a ground plane, so the MOSFETs and the input capacitor represented by these two conductors carrying high DIDT. So with the AC currents, we have an AC magnetic field. This introduces eddy currents in the metal of the ground plane. The eddy currents form a magnetic field that is opposite oriented to the original field, which is good. The current density is highest in the center under the hot loop, but at the edges of our conducting material, it's not zero. So there are remaining currents. The cancellation of the magnetic field of the original loop and from the eddy currents works best. The smaller the distance between the original and the mirror imaged eddy current waveform. So this is the reason why we ask for less than 100 micrometer distance between topside PCB and ground plane. For the system, our PCB shape, connector position and cables usually are determined by the system, but where to place our DC-DC converter. If we recap the in the near field condition, the field strength reduces with an over distance in square. So the magnetic and electric fields go down with distance, and the only thing we can do is move the DC-DC converter block as far away from the connector as possible. This reduces the coupling into the connector and cable and lowers the noise on the cable, and with this we can meet the stringent EMC requirements. Ideally, the EMC filter components are placed close to the connector, and if we have a two-side assembly system, we should consider to place a DC converter block on the opposite side of the PCB with respect to the connector and filter components. In between should be a solid ground copper plane to shield the fields from the converter block into the connector and cable. If we have single-side assembly and a high-density PCB, we have a hard time to find a quiet place to locate our connector and EMC filter components. And very often only a shield is the only solution to meet the EMC requirements. A heatsink can act also as a shield. And whenever we have metal housing, a shield or a heatsink made from metal, we can utilize this to shield part of the fields from the converter. Important is that we provide a return path to the PCB. When it's permitted to have a direct ground connection of the housing to our PCB, we should at least provide an AC connection by using several capacitors in parallel between the shield return and the ground layer. If we have a floating metal like a housing or heatsink or shield, this can act as an antenna. Let's have a close look at the buck converter placement example. Here's a new part, 40 volt 5 amp synchronous buck 4423C. You see the input capacitors are placed very close to the IC. We have a small 042 or 603 type and a larger one with several microfarad next to it. You also see we have a local power ground area that is connected with vias to the ground plane underneath. Here we use the vias to separate the noisy area from our clean system ground. So every via is a little bit of an inductor. You also see that the start of winding of the coil is connected to the switch node. And you see the output capacitors placed next to the inductor. This is done to block part of the E-field radiation from the coil and switch node. We minimize the switch node just to the pad size of the coil in order to reduce the parasitic capacitance. And also we use a very small bootstrap capacitor, as this is connected to switch node. And if it's elevated above PCB, because it's a very big component, it's suboptimum for EMC performance. You also see that VCC bypass capacitor, so this is the output capacitor of the internal linear regulator, is connected directly to the chip on closed traces. This is important as this is supporting the high IDT for the gate driver. You see this black dashed line. This is an area that separates a DC-DC converter block from the rest of the PCB. So it's kind of a fence that tells us inside this block we have noise, and everything outside should be kept clean and separated. In green, you see the shape of the DC-DC converter ground reference block in the layer underneath, so with less than 100 micrometer distance. This area should be larger than the topside area. Whenever possible, we should consider symmetric input capacitor placement. So we have two sets of input caps that are arranged with opposite orientation, so that current loops have fields with opposite orientation, which helps to cancel magnetic field crosstalk into other circuit blocks like the connector or the EMC filters. And this is usually a very strong help for EMC performance. If you look at the multi-layer board, 4-layer PCB, for example, on the top side, we have the components. All the high D IDT and high D VDT components should be placed close together. We use a separation and power ground and system ground to separate the noise from the clean area. We have this in light blue, the solid ground area under the DC-DC block, where we have eddy currents from the hot loops. As the impedance of this of every PCB trace is not zero, this area is pretty noisy due to the high IDT and the finite impedance. At the edges of the board, we have a little bit increased current density and also some magnetic fields. The other thing is that with this approach, we shield most of the noise already with layer 2, and inner layer 2 and bottom layer will be very clean and can act as a clean system reference for connectors and filters. The classic debate, copper under the inductor. Opinion A, no, definitely not. The AC magnetic field from the coil will create eddy currents in the copper under the inductor. This will reduce the effective inductance and create additional losses. The opinion B is, no, directly on top side of the PCB, we should have copper to avoid the magnetic fields from the inductor disturbing the other layers in the PCB. So which opinion is right? Let's have a look. We have a simplified sketch here of a PCB with 4 layers. You see a semi-shielded bobbin type inductor with start of winding connected to the switch. And we have no copper under the inductor in all 4 layers. The simplified magnetic field lines show that we have a lot of magnetic field lines closing around the whole PCB, which means we have coupling into all components, cables and connectors. At the edge of each layer, we have strong eddy currents at the hole, and there's no quiet place in the system to place connector or filter components. The benefit is inductance is not reduced and we have no losses due to eddy currents. Another example is we have solid copper in layer 4. So layer 1, 2, and 3 have a hole under the inductor. In this case, eddy currents will build up in layer 4 and cancel the magnetic field. So under layer 4, there are no AC magnetic field lines anymore from the inductor. So we have a chance to place our filter components and connector, but layer 1, 2, and 3 is still disturbed by the fields from the inductor. Another extreme is to place, the copper directly under the coil in topside layer. In this case, layer 1 will already carry the eddy currents, and layer 2, 3, and 4 will be totally clean. No AC magnetic fields anymore from the coil. This is for system cleanness the best approach, but sometimes other reasons permit this. So whenever we can, we should at least have in layer 2 solid ground under the inductor to make sure that layers 3 and 4 are not disturbed by the inductor magnetic AC fields. Let's have a look on our example case, the MPQ4423C test board. Here's a schematic. We use a 2 microhenry inductor. We have a set of input capacitors, all 0402 or 805, and output capacitors 0805. We have a 2-stage input filter consisting of 2 times 2.2 microhenry coils together with 0805 10 microfarad capacitors and some high frequency capacitor located directly at the connector. Here's a photograph of the PCB. On the top side, you see in the center the IC. The input capacitor C1C, C1B are located very close to the IC. You see a relatively large switch node connecting the inductor, and we have a large area for V out and also a relatively large area for V in. This is also due to the aluminum elco that is placed for damping the input. And on the bottom side, you see the 2-stage input filter consisting of the 2 4x4 by 3 millimeter coils and the ceramic caps. I sketched here already in red the AC current that is flowing in these filter caps, and these capacitors, AC current has a magnetic field that can couple into the other inductor. So we have crosstalk from one stage to the other, and we do not get the damping that we expect from this filter topology. Original on this PCB, there was a larger coil assembled, a 7 by 7 by 5 millimeter, and unfortunately the end of winding that is shown here in this picture was connected to the SW node, and this is suboptimum. I replaced this coil later on with our own MPL AL5030 coil with the start of winding connected to the switch node. So this PCB is in principle pretty good. It has a very small input loop. It has a ground separation between the noisy power ground of the input stage and the reference ground for the connection to the outside world. Disadvantages or suboptimum is a large switch node area, the large V in area, and the large V out area. The EMC conducted emission EMC test result according to CISPA 25 using the automotive OEM limits we see in the low frequency range due to spread spectrum and the 2-stage filter, very low levels. So we have much headroom to the limits, which means we can reduce the size of the filter and the cost. In the high frequency range, 80, 90, 100 megahertz, we see that this board cannot fulfill the automotive OEM limits as is, and this is mainly due to the wrong orientation of the inductor. So in the next step, we turned the inductor and remeasured the conducted emission, and also we changed to the smaller size inductor with the correct orientation which is the curve in green. And you see there's already significant difference, and especially in the high frequency range, just turning the inductor gains 3 dB, which means we are below the target limits. So life is great, and with a smaller inductor we have another improvement. So these are the 3 coils. In the next step, we try to further improve the board by reducing the switch node area. Also the V-out area we made smaller. We removed the pins that were directly connected to the dirty input area for sensing reasons, and we measured at the low frequency conducted emission. The difference is not big, but in high frequencies we see already another 1 dB gain. In a second modification step, we placed 1210 size capacitors next to the inductor. So this is the idea to partly shield E-field radiation of the coil. Actually, on the right side, I only could place a dummy cap which has both sides connected to ground. We also modified the input filter to smaller coils, 1 microhenry and 470 nano. We moved the components a little bit further spaced and placed the final capacitor 1 micro and 22 nano directly at the connector. Doing this, we see in the FM band, the high frequency range, another 2 dB improvement. So here's a summary of our improvement steps. We see in the low frequency range, with a reduced input filter, you have higher amplitude, but still no problem for the limits. So we can save money here and space. And we see step by step how the noise goes down. And this is especially important in the high frequency range. So we see from the initial step is 3 dBs for turning the inductor, and the other modification in total gain another 3 dB. So in total, all these improvements give 6 dB lower noise level in the high frequency range. Another test case was use the same board with 2 megahertz instead of 400 kilohertz. We used the unmodified board. Only the coil was changed to the small 5030 coil with a starter winding at the switch node, and we made the experiment with a transistor heatsink acting as a shield. You see the ground connection on both sides, and here we have the comparison EMC test result in blue without the shield, and in green when the shield is placed. We see already at 2 megahertz and the first harmonic 4 megahertz significant improvement. And especially in the high frequency range, we would have a problem at 2 megahertz meeting the limits, even with a correct coil orientation. But with the shield, we gain almost 15 dB. So this is massive. For comparison, in the test before running at 400 kilohertz with all the little modifications, our best level was around this green bar here, 7 dB microvolt, which is another 5 dB higher than the 2 megahertz using the shield. And there's no need to have a totally closed box shield for the DC-DC converter. We made further experiments checking how important is the grounding of the shield. So we connected the shield both sides to ground. This is a pink result. This is a green result. And we also made an experiment, one side grounded and the shield floating. So it's placed on top of the PCB, but not connected to ground. And you can see there is in the high frequency range still significant improvement. This is due to the fact that the metal carries eddy currents that tend to cancel part of the magnetic field, the crosstalk, but it cannot block the E-field radiation. So the whole shield acts as an antenna. This is why the pink curve is better than without shield, but not as good as the green one where the shield is grounded. And the difference if the shield is grounded on one side or two sides is not visible. So it's the same great performance. For thermal, of course, it's better to have a larger switch node for heat sinking of the coil and transfer from the chip. With a reduced size switch node, the self-heating or the heating up is quicker. And then we have the good news that we open an office, an EMC lab in Ettenheim in Germany, in the southwest Germany. This EMC lab is managed by Jan Sprindler, who also supported strongly this webinar material. We will have a SSC 3-meter chamber for industrial and automotive emission and immunity testing. We also have a CISPA 25 chamber and a shielded chamber for protected emission and immunity testing. And of course, also test places for application engineering, all these pulses and so on. Let's have a look on some frequently asked questions about layout for DC-DC converters. One common question is, can I place the inductor on the opposite side of the PCB with respect to my converter IC? In principle, yes, because the inductor current is continuous waveform with triangular shape, but in fact, it means we will have the noisy switch node on both sides, and whenever we can, well, you should avoid this. So this is only if it's impossible to do it different. So you should avoid this. Question number 2, can I place the input capacitor at the opposite side of the PCB with respect to my IC? This is a clear no. So the most important thing is input capacitors directly at the IC. So this would be a no-go. Why is there an aluminum Elco at VIN? The aluminum Elco at the input has two purposes. One is to damp and stabilize the input node. Damping is because input capacitors are purely ceramic with low ESR, and the input filter inductors form an LC tank circuit that tend to ring at steps and so on, and could lead to overvoltage condition. And with the aluminum Elco with a significant ESR, we damp this, we take the Q out of this LC tank circuit. The second purpose is the aluminum Elco is relatively large in shape and high altitude above PCB, and this can also block part of the E-field radiation from the inductor. So this is a benefit for us. Is there any difference in output filtering for buck and boost topology? Of course, yes. The buck converter output is in principle pretty low noise. Yeah? It has a continuous current from the inductor, which is further filtered by the output capacitor. And boost converter has a fully switched high DIDT output current. The boost converter is more or less a mirror image of the buck converter. So buck converter input is noisy, boost converter output is noisy. So here we have high DIDT. Whenever a cable is connected to boost converter output, we need filtering. Otherwise, we end in an EMC disaster. How about a force switch buck boost? This is the same story. We have a buck on the input, a boost on the output, which means input and output are fully switched with high DIDT. And whenever a cable is connected to a force switch buck boost converter, careful filtering and layout is needed. Shall I connect the analog and power ground directly at the IC or somewhere else? You can connect it at the IC, but usually we do it on the layer underneath. So we use on the top side local islands with vias to the ground reference in the layer underneath. Can I connect my shield or heatsink to a different potential like Vout or VLED plus? Yes, you can. You can connect the heatsink or the shield to a steady potential. And for example, the Vout of a buck converter is a steady potential. It's very low ripple, and the output capacitor act as a return to ground for higher frequency currents. What to do with isolated copper islands in my PCB? During the layout process, you should carefully look that whatever copper islands you have, that they are connected through vias to the ground. If this is not possible, better remove the copper. So this is the end of my presentation. Now you can, Adam will read the questions.
Yeah, no problem. Thank you, Jens. We'll go ahead, as Jens mentioned, and take some time for questions. Just a reminder, just if you could type in your questions into the box located at the bottom of the Zoom control panel, we'll get those answered. So it looks like we have a few questions right now. And the first one is, do you recommend placing a guard ring connected to GND plane along the PCB outline?
Yes, this is always a good idea. Maybe you remember from the slides that I said we have at the edges of our conducting material increased current density, so the current at the edges of the board are not zero, and having a guard ring that is grounded with lots of vias makes sure that this outside of our board is quiet. Yeah, this is definitely the right approach. And actually we should do the same, make a kind of a guard ring around our DC-DC block. This also helps to distinguish between noisy and clean area of our board. It's also like a warning fence. Okay, next one.
Okay, the next question is, are you suggesting to cut the ground under the converter? Do you expect any problems with tracks running over the slots?
So whenever ground cuts are done, you should really carefully think about this. And if traces are routed around the ground cut, this is in principle wrong, because every signal has a return in ground with the opposite direction, and we should provide always a return with minimum loop distance to our signal. So no routings across cuts, unless we have in another layer, adjacent layer, the return for it. Yeah.
Okay, the next question is, what about the shielding effect over the inductor if I connect it to the chassis of my system respect to the GND?
I'm not sure how it is, what's the correct intention of the question. If I place the shielding like I showed it, the heatsink, it will block the magnetic, or part of the magnetic field radiation and a big portion of the E-field radiation. So this makes my chassis even cleaner. The other thing that is important, if this shield is placed too close to my inductor, we have some disadvantages for the losses. So the shield should be placed a couple of millimeters above the inductor. If my chassis is acting as a shield, so my housing for the system, I have to make sure I have an AC return path, and still I might have issues that under my shield or within my housing, I have crosstalk from the DC-DC converter block into my filter components, and then it goes to the cable and I have an EMC problem. So a local shield on top of the inductor or the DC-DC block is better than the global housing, yeah? Because it also avoids a crosstalk on my PCB. Like in every high frequency or tuner system, you have local metal shields. Yeah?
Okay, the next question is, in the case of a two-sided PCB, is it better to place ground plane below the inductor, on the top, or on the bottom of the PCB?
So in principle, I place always ground under the inductor in all layers. If I have a two-layer PCB, then it's very difficult because I need to provide a solid ground, at least with the shape of my DC-DC block, including IC input capacitor and coil output capacitor. If this is the question, so two-layer PCB is much more difficult than four-layer PCB, of course. In general, whenever you can make a ground stripe under the inductor, so between the two pads, if this is possible, yeah? If this is supported by the pad design of the inductor.
Okay, great. The next question is, which point of DC-DC should I connect the board GND plane if the DC-DC is in the middle of the board and is surrounded by other circuitry?
So if the situation is that my DC-DC has to be placed in the center of the board, I would really recommend to have like a ground fence around this block. So concentrate with high density layout the IC, input capacitors, coil, output capacitor in this block, make a ground fence around it, and make the connection in layer 3 of the board. So you connect the output in a like a 4-pole. So you have input and output line with ground in the layer next to it. So typically you would place a local ground in layer 2 under this whole block and have one connection for ground at the input and output, but narrow. And in layer 3, you have the VIN and the VOUT routing. This is all explained in the former webinar from 1.5 years ago. You find it on our website.
Okay, great. And the last question is, what is the suggested distance from the inductor to other inductors of other DC-DC converters on the PCB?
Yeah, this is a good question. Usually, the field goes down with 1 over distance in square. If we are talking crosstalk from one DC-DC converter block into another one, and we have whatever 10 millimeter, 50 millimeter distance, this is not a topic. In general, between converter to converter, it's less problematic than converter into input filter, because if we have crosstalk or magnetic coupling, transformer action from our noisy inductor of the converter into our filter inductor, which should be clean and clean out everything, we do not get the filter effect that we need. Yeah? So to answer your question, the more distance between the filter inductor and the DC-DC inductor, the better. Everything above 20, 30 millimeters is usually significantly low. But ideally, the filter inductor is on the opposite side of the board with respect to the DC-DC converter block.
Great. We have a few other questions that just filtered in. The next one is, why should the start of the inductor winding be connected to the switch node and not at the end of the winding?
Yeah, this is, when you look at the construction of the inductor, I had it in this simplified sketch here. I hope you can still see the presentation. I use this semi-shielded bobbin type inductor as an example, and what I sketched here as a start of winding is connected to the SW node. So with an inductor that has more than one layer of windings, the outer winding that should be connected to the steady potential VOUT is shielding actually the high dVdt from the switch node. You can also think the other way around. The inductor is not a symmetric component. If you look at the standardized symbol, it doesn't show that the inductor is a non-symmetric component, but it is. Of course, it depends a little bit on the construction and the value. If you have only one turn, it's less of a problem. But if you have a 2-layer winding on the core, the parasitic capacitance from start of winding to the environment is much lower than from the end of winding. And that's the point that is important. So it's about the E-field radiation, which means it's a capacitive coupling. Capacitive coupling from the switch node, high dVdt, to the environment is the topic. I hope this is explaining it.
Okay, we've got one other question here. If the IC is far from the power part of each of them, and it has its own GND plane, A GND or P GND respectively, how and where do you connect the 2 ground planes?
So in general, every PCB should have one solid, large ground plane, whole size of the board. That's rule number one. Exceptions of this only if you have very, very good reasons to do this. For example, if you have a very high DIDT motor drive or whatever, which you can clearly separate also from the steering signals from the rest. In 99% of the cases, it's always the best approach in a multi-layer PCB to reserve at least one complete layer as ground, and don't do routing in it, and avoid close density vias with keep outs that create cuts in the ground plane. And from every block you have, you use vias to make the reference to the system ground. This is a safe way. This is the example I explained with the buck converter layer stacking, that we use local areas on the top side to separate the noise from the clean part. But the reference to the system ground is done through vias. So we make sure the whole system has one reference potential. I hope this helps answering the question.
Okay, that looks like that was it for today. That was a good conversation I think we had here at the end. So I'd like to just say thank you to everyone. We appreciate you being here. If you have any further questions regarding today's topic from Jens, please email me. My contact information is located in the invitation that we sent out. And hopefully we'll see you tomorrow, where we will be continuing our webinar series with the topic of solutions for ultra-low power angle sensing. The details you can find on monolithicpower.com. And thank you, Jens, again for your wonderful presentation. We will hopefully see you in a further future presentation soon.
Thanks,
and have a good day. Bye for now.
Have a nice day. Thanks for your time. Bye-bye.